Hello there, and welcome to Space Science Before Sleep, where the universe grows quiet, curiosity moves gently, and science takes its time beneath the stars. Tonight we're going to travel outward from Earth and look for the place where our solar system finally comes to an end. At first that sounds like a simple journey. We picture the sun in the middle, the planets arranged around it, Pluto lingering somewhere near the edge of the old classroom diagram, and then a clean border beyond which interstellar space begins. But nature has not drawn the solar system with the helpful confidence of a textbook illustrator. There is no bright fence waiting beyond the last planet, no final gate, and certainly no sign politely announcing that the sun's neighbourhood has now concluded. Instead, the solar system fades through several different kinds of boundary. The planets end in one region. The solar wind ends much farther away. The sun's gravitational influence continues farther still. So the real question is not simply where the solar system ends, it is what we mean by an ending. From the room around you, the solar system can feel almost comfortably contained. The sun rises, the moon crosses the night, and the planets move like distant lamps against the stars. Even when we imagine the outer worlds, we tend to place them inside a tidy mental circle. Yet that circle is only a diagram, and diagrams have a habit of cleaning up the universe before company arrives. In reality, the solar system is not a flat collection of objects enclosed by one line. It is a set of overlapping regions shaped by motion particles, magnetic fields, and gravity. Some boundaries are defined by what orbits the sun. Others are defined by the stream of charged material flowing away from it. Still others depend on whether the sun's gravity remains strong enough to keep distant icy bodies loosely attached. You do not need to remember every term tonight. Keep only one image in mind, a familiar light behind us, growing smaller as its different forms of influence fade at different rates. Before we drift any farther, I'd love to know where in the world you're listening from tonight and what time it is there. And if these slow journeys through space help you relax, learn something new, or simply feel a little less alone beneath the night sky, I'd be grateful if you liked the video and subscribe to Space Science Before Sleep. It helps this quiet corner reach more curious minds who may need something gentle at the end of the day. If you could travel safely beyond one boundary of the solar system, would you choose the Kuiper Belt, the heliopause, or the distant Oort Cloud? For now, let the question rest beside you. Settle into the pillow, allow the room to grow quiet, and let the details pass without needing to hold them. There is no test waiting at the end of this journey. Missing a name or a number changes nothing. Even falling asleep is simply another way of travelling while the story continues. As we begin, several questions can guide us gently outward. Do the planets mark the true edge or only the end of the most familiar part? If Pluto is not the final object, how far do the frozen worlds continue? Where does the solar wind finally lose its control? How could a spacecraft recognize an invisible boundary when the stars ahead look almost unchanged? Can Voyager be in interstellar space while still remaining within the sun's wider gravitational realm? And can any region have one precise edge when every influence fades in a different way? These questions sound separate, but they all grow from the same hidden distinction. A boundary is not always a wall. Sometimes it is simply the place where one influence becomes weaker than another. Crossing it may change the particles around you, the magnetic environment, or the kinds of orbits that remain stable, while the view through the window would appear almost exactly the same. The most familiar way to define the solar system is by its large planets. Starting near the Sun, we pass Mercury, Venus, Earth, and Mars, then move through the giant planets until Neptune circles in the cold outer dark. Beyond Neptune, sunlight is much weaker, and the Sun itself would appear less like the great disk that warms Earth and more like an extraordinarily bright star. It is tempting to call this the edge, because the grand architecture of the planets has run out, but Neptune is not a border post. Beyond it lies the Kuiper Belt, a broad region containing Pluto and many other icy bodies, along with objects whose stretched or tilted paths carry them through even more distant territory. The region is not packed like an asteroid field in a film. Its objects are separated by immense spaces. Think of a very thin archipelago in a dark ocean, with each island so far from the next that the water seems almost endless. Even here, the solar system is still continuing, and the objects are only part of the story. Long before we reach any supposed final edge, the Sun fills space with a constant outflow of charged particles called the solar wind. This flow carries the Sun's magnetic influence far beyond the major planets and helps form the heliosphere, an enormous region carved into the surrounding interstellar environment. The heliosphere is often described as a bubble, which is useful so long as we remember that it is not round, still transparent plastic, or likely to survive an encounter with soap. Its shape changes as the Sun varies, and as the solar system moves through the thin material between the stars. Somewhere far ahead, that outward flow will slow compress, and eventually meet a boundary called the heliopause. Crossing that boundary can place a spacecraft in interstellar space. Yet even there the Sun's gravity has not vanished. We will discover that the first edge is not the last, and that leaving the Sun's wind is very different from leaving the Sun behind. The last major planet does not stand at the end of the solar system. It stands at the end of the part we learned first. As we move beyond the orbit of Neptune, the familiar arrangement of large worlds begins to fall away behind us. Jupiter and Saturn are now distant memories. Uranus has faded into the darkness, and Neptune itself appears as a small blue sphere moving slowly around a sun that no longer looks large. From this far out, sunlight still dominates the sky, but it has become thinner and colder. The Sun remains dazzling to the eye, yet provides only a small fraction of the warmth received by Earth. The great planetary highway has reached its final major stop. Beyond it, there are no more known giant planets waiting in regular sequence. But the road does not simply end. It becomes quieter, less orderly, and much harder to see. Neptune orbits about 30 times farther from the Sun than Earth does, and one journey around the Sun takes it well over a human lifetime. This is already a useful reminder that the outer solar system moves according to a very different clock. On Earth, seasons arrive, calendars turn, and whole generations pass while Neptune completes only a portion of its path. If you could look back from nearby space, the Sun would appear small enough to cover with a finger, though staring at it would remain a deeply unwise experiment. The planets inside Neptune's orbit would be difficult to separate from the Sun's glare. Earth would be entirely invisible without powerful instruments and precise knowledge of where to look. The solar system we know so well would seem compressed into a tiny bright region behind us, while most of the sky ahead would offer darkness, stars, and distances that refuse to provide any obvious landmark. It is tempting to use Neptune as the edge because it is the outermost major planet, and major planets are the features that dominate most diagrams. Yet diagrams are designed for clarity, not for faithful emptiness. If they showed the real spacing between objects, the planets would become tiny dots scattered across an inconvenient amount of blank paper. Beyond Neptune lies a wide population of smaller worlds, many composed largely of rock and ice. Some follow relatively calm paths around the Sun. Others occupy resonant orbits shaped by Neptune's gravity. Still others travel along stretched and tilted trajectories that carry them far above, below, or beyond the broad plane in which the major planets move. The region does not resemble a neat shelf placed outside Neptune. It is layered, dynamic, and incomplete in our observations. Many of its inhabitants are so faint that sunlight reaches them weakly, reflects from their dark surfaces, and returns to our telescopes as little more than a difficult point of light. Pluto is the most famous of these distant worlds, though fame does not make it the last. It moves through the Kuiper Belt, a broad outer region containing numerous icy bodies left over from the solar system's early history. Some are round enough for their own gravity to shape them. Many are smaller and irregular. A few have moons, thin atmospheres, or surfaces altered by processes that continued long after the inner planets became familiar. Yet the Kuiper Belt should not be imagined as a crowded field of tumbling ice. If we travelled through it, long stretches might pass without a nearby object appearing at all. The best comparison is not a pile of stones, but a very thin archipelago. Each island exists within the same broad region, while enormous dark distances separate one from the next. The name belt makes the place sound conveniently organised. The actual universe has once again declined to arrange itself for an educational poster. As we travel farther, the distinction between the Kuiper Belt and the regions beyond it becomes less like crossing a border and more like watching one population gradually give way to another. Some objects have orbits strongly influenced by Neptune. Others wander much farther from the Sun before returning. Their paths can be highly elongated, carrying them through remote spaces where sunlight becomes extraordinarily weak. Astronomers often group these objects according to their orbital behaviour, but nature does not label them while they travel. The categories help us understand how the outer solar system may have formed and changed. They also reveal that the region beyond Neptune is not a preserved museum. Gravitational encounters, slow orbital shifts, and the early migration of the giant planets have left patterns in the paths we observe today. Each small world is therefore more than a frozen remnant. Its orbit is a record written in motion of events that occurred when the solar system was young. So where are we now? We have passed the last major planet, but we have not passed the last body orbiting the Sun. We have entered a realm where worlds become smaller, distances grow wider, and the familiar architecture of the planets dissolves into scattered populations. Even this region is not the final gravitational frontier. Far beyond it, still more distant objects may remain loosely bound to the Sun, and all around us invisible to the eye. The solar wind continues to flow outward through the darkness. The planets may have given way, but the Sun has not finished shaping the space around them. To find the next boundary, we must stop looking only for worlds and begin looking for something far less visible. The vast moving atmosphere of particles and magnetic fields that surrounds the entire planetary system. Beyond the last major planet, the solar system becomes less visible but no less interesting. The darkness ahead is not arranged around one final world. Instead, it contains a broad frontier of frozen bodies moving along paths that preserve traces of the solar system's distant past. Some remain within a relatively calm belt beyond Neptune. Others follow tilted or stretched orbits that carry them far outside the region where most planets travel. From a distance, this population might look like a faint disk surrounding the Sun. Up close, there would be almost nothing to see for long periods at a time. The objects are small, the gaps between them are enormous, and most reflect very little sunlight back toward us. Yet this sparse frontier is not merely leftover debris. It is an archive written in ice and orbital motion, storing evidence of a time when the planets themselves were still shifting into place. The Kuiper Belt begins beyond Neptune and occupies a wide band around the Sun rather than a narrow ring. Its members include mixtures of frozen substances and rock, although their exact compositions differ from one object to another. Water ice is common, while more volatile materials can survive on some surfaces because the region is so cold. Pluto is its most familiar resident, but it is one member of a much larger population that includes other dwarf planets and countless smaller bodies. The word belt can make the region sound crowded, perhaps like stones filling a roadway. In reality, a traveller could cross vast distances without passing close to anything at all. Even a collision between two small objects would be a remarkable event rather than part of the daily traffic. The Kuiper Belt is therefore best pictured as a very thin field of distant islands, each following its own path through an ocean of darkness. Those paths are shaped strongly by Neptune. Although the planet lies inward from much of the Kuiper Belt, its gravity reaches outward and organizes some bodies into stable orbital rhythms called resonances. Pluto provides the best-known example. Neptune completes 3 journeys around the Sun during the time Pluto completes 2, creating a repeating pattern that prevents dangerous close approaches between them. Their orbits cross in a flat diagram, but the timing and geometry of their motion keep the two worlds safely separated. It is a little like two travellers using the same junction on perfectly coordinated schedules, although celestial mechanics achieves this without clocks, traffic lights, or anyone becoming annoyed about right of way. Other Kuiper Belt objects occupy different resonances with Neptune. By studying these patterns, astronomers can work backward and test ideas about how Neptune may have migrated during the solar system's early history, carrying or trapping smaller bodies as its orbit changed. Not every object beyond Neptune belongs to the same calm arrangement. Some occupy what astronomers call the classical Kuiper Belt, following comparatively stable paths that avoid strong present-day encounters with Neptune. Others belong to dynamically excited populations with more tilted or elongated orbits. The differences matter because an orbit can preserve a record of earlier gravitational disturbance. A small body may have been scattered outward by a giant planet trapped into a resonance, or left in a region where its orbit remained stable for billions of years. The surfaces of these worlds preserve a different kind of history. Some appear dark, while others show reddish colouring that may come from complex carbon-rich material altered by radiation. A few are large enough for gravity to pull them into rounded shapes. Some have moons. Pluto itself has mountains of water ice, broad plains of frozen nitrogen, and an atmosphere that changes as it travels along its orbit. The outer frontier is cold, but it is not geologically or chemically featureless. Farther outward, the scattered disk overlaps the outer part of the Kuiper Belt and extends into a much larger volume. Its objects often travel on highly elongated orbits approaching Neptune's region at one part of their journey and retreating far into the darkness at another. The dwarf planet Eris is one notable member of this wider population. Other distant bodies follow paths that are even more detached from Neptune's immediate control, raising questions about how their unusual orbits were produced. Some may record ancient encounters among the giant planets. Others may have been influenced by passing stars when the young sun still lived among its stellar siblings. Astronomers have also investigated whether an undiscovered distant planet could help explain some orbital patterns, but no such world has been confirmed. The important point is not that one dramatic explanation has won. It is that the outer solar system still contains enough unseen territory for several ideas to remain under careful examination. Our map of this region is incomplete because distance makes discovery difficult. A small body far from the Sun receives little light and returns even less to Earth. Detecting it may require repeated images taken over time, allowing astronomers to notice a faint point that moves slightly against the background stars. Objects near the distant parts of elongated orbits can become especially hard to find, which means the population we know is shaped partly by where our surveys have looked and what they were capable of detecting. The boundary of the icy frontier is therefore not drawn only by nature. It is also drawn temporarily by the limits of our instruments. Beyond the known belt and scattered populations, the gaps grow wider and the evidence becomes more indirect. But while visible worlds become rarer, the surrounding space is still filled by something flowing continuously from the Sun. To understand the next ending of the solar system, we must leave the frozen islands behind and begin following that invisible wind. The frozen worlds do not define the Sun's farthest reach. Long after Neptune has faded behind us, and long after the scattered islands of the Kuiper Belt have become too distant to see, we are still travelling through an environment created by our star. It has no visible ceiling and no surface beneath it. There is no warm golden glow filling the darkness. Yet particles released from the Sun continue streaming past us, accompanied by magnetic fields that connect this remote region to events occurring far behind near the solar surface. In that sense, the planets exist inside something much larger than the planetary system shown in familiar diagrams. They are surrounded by the Sun's extended atmosphere, an enormous and restless domain called the heliosphere. We cannot see its full shape from where we are, but every planet-moon spacecraft and icy body we have passed so far has spent its existence within it. The material forming this domain begins much closer to the Sun in its outer atmosphere or corona. The corona is so hot that some of its particles move fast enough to escape the Sun's immediate pull and continue outward into space. This flow is called the solar wind. It consists mainly of electrons and protons along with smaller amounts of other charged particles. Together these particles form a plasma, a state of matter in which electric and magnetic forces become especially important. The word wind is helpful because the material flows outward, but it should not make us picture air moving through a terrestrial sky. There is no ordinary atmosphere here, and the solar wind is far more sparse than anything we would experience as weather on Earth. Even so, it crosses immense distances, surrounds planets, shapes magnetic environments, and continues beyond the region occupied by the major worlds. Thin does not mean unimportant. Space has plenty of room for subtle influences to become enormous. The solar wind does not leave the Sun at one unchanging speed or with one perfectly smooth structure. Different regions of the corona can produce faster or slower flows, and solar activity can send concentrated clouds of plasma outward through the heliosphere. As the Sun rotates, its magnetic field is carried with this moving material and becomes wound into a vast spiral pattern. Imagine a slowly turning garden sprinkler sending water outward while the streams curve across the lawn. The comparison helps us picture the geometry. Although the Sun is not spraying liquid, the magnetic field is not a rigid tube, and the lawn would need to be somewhat larger than good planning regulations usually permit. Earth and the other planets move through this changing magnetic environment as they orbit. Auroras, disturbances in planetary magnetic fields, and some forms of space weather are nearby expressions of a much larger connection extending through the solar system. From our distant position beyond Neptune, the sunlight and the solar wind tell two different stories. Visible light has been spreading outward since leaving the Sun, growing weaker as it is distributed across an ever larger area. The solar wind also becomes less dense with distance, but it remains a moving plasma whose behavior depends on pressure magnetic fields and its interaction with the material between the stars. Gravity tells a different story again. It weakens with distance but does not travel outward as a stream of particles. These influences overlap, yet they should not be treated as one thing. The region filled and shaped by the solar wind is the heliosphere. It is not simply the region where sunlight exists because sunlight continues far beyond it. Nor is it the entire region where the Sun's gravity matters, because gravity reaches much farther than the solar wind boundary. One star can therefore possess several different kinds of reach, each fading according to different rules. The heliosphere is often shown as a glowing bubble surrounding the planets. This is a useful first image, but it can become misleading if we imagine a perfect sphere with a thin and polished surface. The solar system is moving through the local interstellar medium, a sparse mixture of particles and magnetic fields belonging to the wider Milky Way. The solar wind pushes outward, while this surrounding environment presses inward. The result is a vast, changing structure shaped by the strength of the solar wind, the sun's magnetic activity, the direction of the interstellar magnetic field, and the motion of surrounding material. Scientists must reconstruct much of its global form from measurements made inside it, observations of particles arriving from its distant boundaries and the limited paths followed by spacecraft. Looking outward from within the heliosphere is rather like trying to determine the shape of an entire fog bank while standing somewhere inside the fog. The view contains clues, but not a convenient aerial photograph. Keep one simple image in mind as we continue. Behind us, the Sun has become a brilliant point far smaller in appearance than it was from Earth. Around us, the planets are no longer visible, and nearby icy worlds are unlikely to interrupt the darkness. Yet an invisible flow still moves past, carrying particles and magnetic structure away from the Sun. Ahead, the pressure of the surrounding interstellar environment becomes increasingly important. The solar wind cannot expand freely forever. As it travels farther, it thins, cools, and approaches a region where its rapid outward motion must change. There will still be no wall and no sudden change in the stars. Instead, the wind will begin to slow as the influence of the galaxy presses more firmly against the influence of the Sun. Our next boundary is the place where that slowing becomes unavoidable. The solar wind does not stop when the planets disappear. It keeps moving outward, thinner than before, but still fast carrying particles and magnetic structure into a region where the pressure of the surrounding galaxy can no longer be ignored. For most of its journey through the planetary system, this flow travels faster than disturbances can move back through the plasma and warn it about conditions ahead. In that limited sense, it is supersonic, although there is no ordinary air here and no human ear waiting to hear it. The relevant waves travel through electrically charged matter and magnetic fields, rather than through the atmosphere of a room. The particles have crossed billions of kilometers, while the flow has continued expanding, and by now the solar wind is far less dense than it was near Earth. Even so, speed and low density allow it to maintain an outward pressure across an astonishing volume. Far from the Sun, however, the flow approaches a place where it must adjust. It cannot continue expanding at the same speed and in the same state forever. The change begins at a broad invisible boundary called the termination shock. The name sounds more dramatic than the view would be. A traveller crossing the termination shock would not encounter a solid surface, a flash of light, or a cosmic speed bump thoughtfully installed in the darkness. The stars would remain in their familiar positions, and the distant Sun would still shine behind us. What changes is the behaviour of the plasma. The solar wind slows, abruptly becomes compressed, and grows hotter as part of its organised outward motion is converted into more disordered particle motion. Before the boundary, the flow is racing outward faster than important pressure signals can travel through it. Afterward, those disturbances can move through the slower plasma more effectively. The result resembles a shock wave, but not one formed by an explosion striking a wall. It is a transition created because the solar wind is being forced to respond to the pressure of the environment beyond the Sun's immediate domain. A useful earthly comparison is traffic approaching a crowded junction. Cars may travel freely along an open road, then slow and bunch together as conditions ahead become restrictive. The termination shock also involves a fast flow becoming slower and denser. But the comparison ends quickly. Solar wind particles do not remain politely in lanes, they do not press brake pedals, and magnetic fields play a role for which most road systems have wisely declined responsibility. Another comparison is water passing through a sudden hydraulic jump, where a fast shallow flow becomes slower and deeper. Again, the image is only partial. The outer heliosphere is a plasma environment shaped by charged particles, magnetic fields, energetic neutral atoms, and particles picked up from interstellar space. The science becomes complicated precisely because several populations share the same region, while exchanging energy in ways that ordinary fluids cannot fully reproduce. The termination shock is not a perfect sphere centered neatly on the Sun. Its position depends on a balance of pressures, and those pressures change. The solar wind varies with solar activity. Large disturbances can travel outward from the inner solar system and alter conditions far away, although they need considerable time to arrive. At the same time, the local interstellar medium presses against the heliosphere from outside, while its magnetic field helps shape the boundary. The entire structure is therefore capable of moving inward or outward, and one direction need not match another. The two Voyager spacecraft encountered the termination shock at different distances along different paths, offering direct evidence that the boundary is not a motionless shell. A neat diagram may place it at one convenient radius, but the real boundary shifts, bends, and responds. Even the word boundary can make it sound more precise than it is. In practice, a spacecraft measures a transition through changing particles, fields, speeds, and energies. The universe rarely draws a thin line when a complicated region will do. Let us pause here at the first major change in the Sun's distant wind. Behind us lies the enormous inner heliosphere containing Earth, every major planet, and the icy frontier beyond Neptune. Ahead lies a region where the solar wind has lost much of its earlier speed but has not yet surrendered its identity. The particles still come largely from the Sun. The magnetic field still carries a solar history, yet the surrounding interstellar environment is becoming increasingly influential. We have not crossed into interstellar space, and we have not reached the heliopause. We have only entered the outer layer where the contest between solar and galactic conditions becomes impossible to overlook. This is why the termination shock cannot serve as the final edge of the solar system. It marks a transformation within the heliosphere, not the end of the heliosphere itself. Beyond this transition stretches the heliosheath, a broad region of slower, compressed and disturbed solar plasma. It is not a narrow corridor between two clean surfaces. Its structure changes with time and direction, and our knowledge of it comes from limited spacecraft paths combined with remote measurements and physical models. From the safety of imagination, we can continue through it without feeling the particles or the magnetic turbulence around us. The scene remains dark and almost perfectly still to human eyes. Yet scientifically, the environment has become more restless. Solar material is being redirected, compressed and reshaped as it approaches the outer boundary of the heliosphere. The wind has slowed, but the journey has not. We are now entering the long transition between the Sun's familiar outward flow and the interstellar space waiting beyond. The heliosheath is not the end of the Sun's influence. It is the place where that influence becomes compressed, redirected, and increasingly difficult to separate from the environment beyond. After crossing the termination shock, the solar wind no longer races outward in the same fast and orderly way. Its particles move more slowly as a bulk flow, yet their individual motions become more energetic and disordered. Magnetic fields bend and fluctuate. Different particle populations pass through one another. The pressure of the surrounding interstellar medium becomes steadily more important. To human eyes, the scene would remain almost perfectly dark. There would be no glowing fog, no visible storm, and no obvious sign that we had entered a more complicated region. But instruments would tell a different story. The quiet darkness is filled with changing particles, shifting magnetic fields, and plasma that has begun to turn away from its direct path outward. We've entered the heliosheath, the broad outer layer between the termination shock and the heliopause. The solar wind arriving here has already travelled across the planetary system, carrying material and magnetic structure from the Sun. At the termination shock, much of its forward speed was reduced. Inside the heliosheath, the flow continues moving, but it must now find a path around the pressure of the interstellar environment. Some of it is diverted sideways. Some may be carried into extended regions downstream from the Sun's motion through the galaxy. The entire process changes with direction and time, so there is no single pattern that applies everywhere. An illustration may show the heliosheath as a smooth layer wrapped around a tidy bubble, but the real region is disturbed and uneven. A useful image is the water behind a slowly moving boat, where the flow is redirected and mixed into a broad wake. Yet the comparison has limits. Plasma responds to magnetic fields, and neutral atoms can cross through regions that charged particles cannot enter as easily. The outer heliosphere is less like ordinary water and more like several invisible fluids sharing the same space while following different rules. One of the most important particle populations here begins outside the heliosphere. Neutral atoms from the local interstellar medium can move inward because they carry no electric charge and are therefore not guided directly by magnetic fields. Some of these atoms eventually lose an electron and become charged. Once that happens, they are caught by the solar wind's magnetic environment and gradually brought into its motion. Scientists call them pick-up ions because the solar wind effectively picks them up along the way. By the time the flow reaches the termination shock and heliosheath, these particles can hold a substantial part of the energy in the plasma. This makes the region more complicated than a simple wind slowing against outside pressure. It contains material born from the Sun, material that entered from interstellar space, and particles that have changed identity while travelling between the two. The boundary is already becoming permeable before we reach its outermost edge. The heliosheath also contains energetic particles that reveal how restless this apparently still region can be. Some are accelerated through interactions involving shocks, magnetic fields, and turbulent plasma. Their behavior helped the Voyager spacecraft recognize that they had entered a new environment after passing the termination shock. Yet Voyager 1 and Voyager 2 did not travel side by side. They moved outward in different directions, crossed boundaries at different distances, and sampled different portions of the heliosheath. Their measurements, therefore, provide two narrow paths through an enormous three-dimensional structure. It is rather like sending two tiny boats across different parts of a vast changing sea, and then asking them to describe the shape of every current. Their reports are invaluable, but they cannot show the whole ocean. Scientists combine those measurements with observations from nearer Earth computer models and particles arriving from distant parts of the heliosphere to build a broader picture. Some of those particles are energetic neutral atoms. They are created when a fast charge particle captures an electron from a neutral atom. Once electrically neutral, the particle is no longer tied to the surrounding magnetic field in the same way, and may travel in a nearly straight line. If it reaches an instrument near Earth, its direction can offer a clue about the distant region where it formed. In this way, scientists can construct maps of interactions near the outer heliosphere without placing a spacecraft at every point. The method resembles learning the shape of a hidden landscape by catching messengers arriving from different directions. But each messenger carries limited information, and interpreting the map requires models of how the particles were created and what happened during their journey. These observations have revealed that the outer heliosphere contains unexpected structure. They have also reminded scientists that a glowing model on a screen is a reconstruction, not a photograph taken from outside. As we continue through the heliosheath, the influence of the interstellar environment grows stronger. The solar plasma is still present around us, but it is no longer expanding freely. Its motion has slowed, its direction is changing, and its magnetic structure is being pressed into new forms. The thickness of this region is not the same in every direction, and it can change as the sun's activity varies. Disturbances launched near the sun may take a long time to reach this distant boundary, but they can still alter the balance when they arrive. The heliosheath therefore remembers events from the inner solar system long after those events have faded from the skies of Earth. Gravity continues working patiently, and the solar wind continues carrying old news outward. The outer solar system keeps a very slow schedule. Ahead lies the heliopause, the boundary most often associated with the beginning of interstellar space. Even now it does not appear as a wall. The stars do not gather around it, and the darkness does not change colour. Yet the dominant origin of the plasma around us is approaching a transition. On one side, the environment is shaped mainly by the slowed solar wind. On the other, the surrounding material belongs mainly to the space between the stars. The boundary can move ripple and respond to changing pressure. Some particles may cross it while others are redirected. We are nearing the place where the sun's wind finally gives way, but not where sunlight ends, and certainly not where gravity disappears. The next edge will be scientifically real, physically subtle, and completely invisible to the eye. The heliopause is a real boundary, but it is not a wall. As we approach it from within the heliosheath, nothing visible gathers ahead of us. There is no shining membrane stretched across the stars, no sudden darkness, and no final surface waiting to be touched. The distant sun remains a brilliant point behind us, while the surrounding sky looks much as it did moments before. Yet the plasma environment is nearing an important change. On our side, the particles and magnetic structure have been shaped mainly by the solar wind, even though that wind has slowed and become disturbed. Beyond the boundary, the surrounding plasma belongs mainly to the local interstellar medium. The heliopause is therefore not the place where matter ends. It is the place where the balance between two vast environments shifts. One influence stops dominating, and another takes over. That balance is created by pressure. The solar wind pushes outward from the sun while the interstellar medium presses against the heliosphere from outside. Neither side behaves like a rigid object. Both contain thin plasma-moving particles, magnetic fields, and neutral atoms. Where their pressures reach a changing balance, the heliopause forms. A useful comparison is the meeting place of two ocean currents. Crossing from one current into another does not require passing through a solid barrier. The water continues, but its direction, temperature, or origin may change. The heliopause works in a similarly gradual way, although plasma and magnetic fields add layers of behavior that ordinary currents do not possess. The boundary may be narrow in some measurements and more complicated in others. It can bend, ripple, and move as conditions change on either side. The solar system has once again avoided the administrative convenience of a permanent border. The heliopause is also selective rather than perfectly sealed. Charged particles respond strongly to magnetic fields, so many of them are redirected as they approach the boundary. Neutral atoms carrying no net electric charge can cross more freely. Some interstellar atoms enter the heliosphere and travel deep toward the sun before interacting with the solar wind. At the same time, energetic particles created within the heliosphere may move outward, and some particles from interstellar space can penetrate inward. This exchange does not erase the boundary. Instead, it shows that a scientific boundary can remain meaningful, even when material passes through it. The open door of a house still separates indoors from outdoors even while airlight and visitors cross the threshold. In the heliosphere, however, the door has no hinges, the house is moving through the galaxy, and the threshold may shift while we are trying to measure it. Solar activity can help move that threshold. The sun does not release a perfectly steady wind. Its output changes over time, and large disturbances can travel outward through the heliosphere. By the time they reach this distant region, months or longer may have passed, but they can still alter pressure near the boundary. The local interstellar environment also varies, and its magnetic field helps shape the heliopause. This means that the boundary encountered by a spacecraft is not guaranteed to remain at the same distance. It may expand outward when solar pressure grows stronger, or retreat inward when that pressure weakens. Its location also differs according to direction. A spacecraft traveling along one path may reach it sooner than another moving elsewhere. There is no single radius that captures the entire shape. A number can describe one crossing at one place during one period. It cannot serve as a permanent measurement for the whole heliosphere. Crossing the heliopause changes the meaning of the phrase interstellar space. Inside the heliosphere, even far beyond the planets, the surrounding plasma is still dominated by material flowing from the sun. Outside, the plasma environment is primarily associated with the space between stars, but sunlight continues through both regions. The sun's gravity continues through both regions. A spacecraft does not suddenly become free of every solar connection, merely because the solar wind is no longer the dominant plasma around it. Radio signals can still travel between the spacecraft and Earth. The sun still appears brighter than every other star. Its gravitational pull, though weak at such a distance, is not switched off. Crossing the heliopause is therefore a major scientific transition, but only one kind of departure. We've left the sun's wind-dominated domain. We have not yet escaped every way in which the sun shapes our journey. From the safety of imagination, let us pass through the boundary now. The crossing offers no visible spectacle. The spacecraft does not shake, and the stars do not rearrange themselves. Only the instruments begin to report that the surrounding conditions have changed. Certain particles associated with the solar wind decline. Galactic cosmic rays become more common. Plasma measurements reveal a different environment. Magnetic observations add another part of the picture, although the results are not always as simple as early diagrams might suggest. The transition must be recognized through several measurements considered together. It is less like seeing a border, and more like realizing that the weather, air pressure, and direction of the wind have all changed while the landscape remains dark. This is the quiet strangeness of the heliopause. It is among the most important boundaries crossed by a human-made object, yet it offers almost nothing for human eyes to see. Its existence is revealed by particles too small to notice fields that remain invisible and signals sent home across billions of kilometers. 2 Voyager spacecraft eventually reached this region along different paths, carrying instruments built decades before their crossings occurred. They did not encounter a gate announcing their arrival in interstellar space. Instead, scientists had to listen carefully to what the surrounding plasma and particles were saying. Our next question is therefore not where the boundary was, but how anyone could know that Voyager had crossed it. Voyager did not recognize interstellar space by seeing it. The spacecraft crossed an invisible boundary. While the stars remained unchanged, the distant sun continued shining, and no instrument produced a cheerful message announcing that the solar system's outer atmosphere had been left behind. Instead, scientists had to compare several quiet changes in the surrounding environment. Particles associated with the heliosphere became less common. Galactic cosmic rays became more abundant. The density of the plasma changed. Magnetic measurements offered clues, though not always the clues researchers had expected. Only when these pieces were considered together could the crossing be identified with confidence. The heliopause was not detected as one dramatic event. It emerged gradually from data sent across billions of kilometers by machines designed in the 1970s, when their eventual arrival in interstellar space belonged to a future almost too distant to plan comfortably. Voyager 1 reached the boundary first. During 2012, its instruments recorded a series of changes as the spacecraft approached the outer edge of the heliosphere. The number of lower-energy particles arriving from inside the solar system began to fall, sometimes recovering before falling again. Meanwhile, higher-energy particles arriving from the wider galaxy became more common. These galactic cosmic rays had been partly deflected by the heliosphere, so their increase suggested that Voyager was entering a region less protected by the Sun's magnetic environment. The measurements did not change only once. They rose and fell through a complicated transition, as though the spacecraft were moving near a shifting shoreline while tides repeatedly covered and uncovered the same ground. Then in August 2012, the population of heliospheric particles dropped sharply and remained low, while galactic cosmic rays rose and stayed elevated. Something fundamental around the spacecraft had changed. Even then, scientists remained careful. One expected sign of the crossing was a clear change in the direction of the magnetic field. The interstellar magnetic field outside the heliosphere was thought likely to point in a noticeably different direction from the field carried outward by the solar wind. Yet Voyager 1 measured a magnetic field that became stronger without immediately turning as much as some models had predicted. This created uncertainty. Had the spacecraft truly entered interstellar space, or had it reached an unfamiliar outer layer still connected to the heliosphere? Science is often described as a sequence of discoveries, but it is just as often a sequence of people refusing to celebrate until the instruments stop offering alternative explanations. The boundary had not behaved according to the neatest expectation, so the evidence had to be examined more closely. A decisive clue came from the plasma surrounding Voyager 1. The spacecraft's original plasma instrument had stopped working decades earlier, which meant it could not directly measure the density of the material around it in the usual way. But Voyager still carried a plasma wave instrument capable of detecting oscillations in charged particles. When disturbances from solar activity eventually reached the spacecraft, they caused the local plasma to vibrate. The frequency of those vibrations allowed scientists to estimate the electron density. The result indicated that Voyager was surrounded by plasma much denser than the weakened solar wind expected inside the outer heliosphere. It matched the kind of density anticipated in the local interstellar medium. By tracing later measurements backward, researchers concluded that Voyager 1 had crossed the heliopause on August 25, 2012. The spacecraft had entered interstellar space, even though one expected magnetic change had been far more subtle than anticipated. Voyager 2 reached the heliopause along a different path in November 2018. This second crossing was especially valuable because Voyager 2 still had a functioning plasma science instrument. It could directly measure the speed, density, temperature, and pressure of the surrounding plasma. As the spacecraft approached the boundary, the outward solar wind flow weakened and then disappeared from the instrument's measurements. At the same time, heliospheric particles declined and galactic cosmic rays increased. The magnetic field became stronger, and other instruments recorded changes consistent with the transition into the interstellar medium. Voyager 2 therefore supplied a somewhat different collection of evidence from Voyager 1. The two spacecraft agreed on the broad story, but they did not encounter identical boundary conditions. This was not surprising. They crossed in different directions at different times in the solar cycle. through a heliopause that shifts as pressures change. The crossings also showed that the heliopause is not perfectly sealed. Voyager measurements detected particles moving in both directions near the boundary. Some particles from the heliosphere reached outward, while some galactic particles entered inward. The transition contained layered structures and temporary changes rather than one mathematically thin surface. A useful comparison is recognizing that a ship has entered a new current by measuring the water around it. The direction of drifting objects changes, the temperature shifts, the chemistry differs slightly, yet no painted stripe lies across the sea. Voyager recognized interstellar space in much the same way, except its sea was almost empty. Plasma, its compass, included magnetic field sensors, and each measurement required hours for its radio signal to reach Earth. Cosmic exploration rarely offers immediate paperwork. These two crossings gave humanity its first direct measurements from the interstellar medium beyond the heliopause, but they remain only two narrow tracks through an enormous and changing boundary. Voyager 1 did not travel through the same region as Voyager 2, and neither spacecraft can reveal the full three-dimensional shape of the heliosphere. Their observations are more like two threads drawn through a vast invisible fabric. Scientists combine those threads with measurements made nearer Earth observations of energetic neutral atoms and computer models to understand the larger structure. What Voyager established was not the exact shape of every distant boundary, but something simpler and more profound. Human instruments had travelled far enough for the particles around them to belong primarily to the space between stars, and yet the crossing did not place Voyager in emptiness. Beyond the heliopause, atoms still drift magnetic fields, still curve through space dust grains, continue along ancient paths, and energetic particles arrive from distant regions of the galaxy. The spacecraft had left the Sun's wind-dominated environment, but it had entered another environment rather than leaving matter behind altogether. To understand what truly lies beyond this edge, we must now look closely at interstellar space itself, a region that appears almost perfectly vacant and is anything but completely empty. Interstellar space is not empty. It only appears empty because its matter is spread so thinly that human senses would find almost nothing to notice. Beyond the heliopause there is no floor beneath us, no atmosphere pressing against a window, and no visible cloud stretching from star to star. Yet atoms drift through the darkness. Charged particles move along magnetic fields. Tiny grains of dust cross enormous distances. High-energy cosmic rays arrive from violent events elsewhere in the galaxy. The region Voyager entered is therefore not an absence of everything. It is a different kind of environment, one governed less by the solar wind, and more by the material filling the space between stars. The change is subtle enough to be invisible, but real enough for instruments to measure. Beyond the Sun's outer plasma boundary, the Milky Way has already begun to make its presence felt. Most of the ordinary matter in the interstellar medium exists as gas with hydrogen, by far the most common element, and helium making up much of what remains. Some atoms are neutral, carrying no overall electric charge. Others have lost electrons and become ions, creating plasma mixed with free electrons. The proportions vary from place to place. In some regions, the gas is relatively cool and neutral. Elsewhere, radiation from hot stars or ancient stellar explosions has heated and ionized it. The solar system currently moves through a local environment containing both neutral and charged material, but this region is not uniform or permanent. Over astronomical time, the Sun travels through different parts of the galaxy, each with its own density, temperature, and magnetic conditions. Our heliosphere is therefore not expanding into one unchanging background. It is moving through a galactic landscape whose features are almost entirely invisible to the eye. The material is extraordinarily sparse by earthly standards. A volume that would contain an enormous number of molecules near sea level might hold only a handful of particles in interstellar space. From the viewpoint of a person, that sounds close enough to nothing. Across distances measured in light years, however, even a thin gas can absorb, scatter, emit, and redirect enough light to reveal itself. Astronomers detect interstellar matter by studying the colours and spectra of stars behind it. Certain wavelengths are absorbed by particular atoms or molecules, leaving narrow signatures in the starlight. Dust can dim distant objects and make them appear redder, because shorter wavelengths are scattered more effectively. Empty-looking space therefore leaves fingerprints on every beam of light that passes through it. A single atom is easy to overlook. An entire light year gives it plenty of company. Interstellar dust contributes only a small fraction of the medium's mass, yet it has an influence far greater than its modest quantity might suggest. These grains are not usually soft household dust, waiting patiently beneath cosmic furniture. They are tiny solid particles containing materials such as silicates, carbon-rich compounds, and frozen coatings in sufficiently cold regions. Dust blocks visible light, helps cool clouds of gas, and provides surfaces on which simple molecules can form. In denser interstellar clouds, gas and dust may eventually become part of new stars, planets, comets, and perhaps the raw chemistry of future living systems. Some grains also travel into the heliosphere, where spacecraft instruments can detect them directly. The space between stars is therefore not merely the gap separating completed solar systems. It contains material that can be recycled into solar systems that do not yet exist. Magnetic fields thread through this environment as well. They are weak compared with the fields close to planets or laboratory magnets, but they extend across enormous regions and influence charged particles over long periods. Plasma does not move independently of these fields. The two interact, bend, compress, and carry energy through the interstellar medium. Near the heliopause, the local interstellar magnetic field helps shape the outer boundary of the heliosphere. It can redirect charged particles and affect how the solar and interstellar environments meet. Neutral atoms respond differently because they do not carry a net charge, allowing some of them to cross the magnetic boundary more freely. This is one reason the heliopause cannot be understood as a sealed shell. The space outside presses against it, threads magnetic influence around it, and sends neutral material through it. Cosmic rays add another nearly invisible population. Despite the name, most are not rays of light but energetic atomic nuclei, and other particles moving through the galaxy at very high speeds. Some are associated with powerful stellar processes, including supernova remnants, although their complete origin spans several kinds of sources and remain an active area of research. The heliosphere helps deflect and modify part of this galactic particle population, so spacecraft generally detect more galactic cosmic rays after crossing the heliopause. Even then, the environment is not suddenly filled with a brilliant storm. The particles remain sparse. Their importance comes from their energy, their ability to penetrate matter, and the information they carry about distant astrophysical events. Interstellar space is quiet only when measured by sound. In particles and fields, it is continually receiving old messages from across the Milky Way. It is also important not to confuse interstellar space with intergalactic space. Interstellar space lies between stars inside a galaxy. It still belongs to the Milky Way's disk clouds, magnetic environment, radiation fields, and gravitational structure. Intergalactic space lies between galaxies on a much larger scale and is generally even more rarefied, although it too contains matter. Voyager has not left the Milky Way and will not approach its outer boundary on any remotely human timescale. It has simply crossed from a region dominated by the sun's wind into the nearby material through which the entire solar system is moving. The galaxy was never waiting somewhere far beyond the solar system. It was already surrounding it, so the darkness outside the heliopause is not a blank page. It contains gas that can be measured through starlight dust that once belonged to older stars, energetic particles travelling from distant events and magnetic fields that help shape the sun's outer domain. All of this material presses against the heliosphere as the solar system moves through the galaxy. The boundary we crossed exists because these two environments meet. To understand the heliosphere's shape, we must now stop picturing the sun as motionless at the centre of a perfect bubble. The entire solar system is travelling through the interstellar medium, carrying its invisible shelter with it. The heliosphere does not sit motionless while the galaxy flows around it. The sun, the planets, the distant icy bodies and every spacecraft we have sent outward are all travelling together through the Milky Way. As this moving system passes through the local interstellar medium, the solar wind pushes outward while surrounding particles and magnetic fields press inward. The result is often illustrated as a bubble carried through space, perhaps with a rounded front and a long tail stretching behind it. That image is useful, but it is not a photograph, and the true shape may be far more complicated. The heliosphere can expand, contract, ripple, and respond to conditions arriving from both directions. Changes begin near the sun and travel outward. Interstellar material presses inward from the galaxy. Between them lies a boundary that is never entirely finished. We can begin with the image of a boat moving through water. The bow pushes into the flow ahead while disturbed water extends behind it. In a similar way, the sun moves relative to nearby interstellar material, and the heliosphere may develop different structures in the direction of travel and farther downstream. But the comparison soon becomes unreliable. The surrounding medium is not ordinary water. It contains neutral atoms, plasma energetic particles and magnetic fields, all interacting according to different rules. The solar wind is also not steady. Its speed and density vary across the sun and throughout the solar cycle. Instead of a simple boat crossing a calm lake, imagine a boat that changes the strength of its engine while moving through water threaded with invisible elastic currents. The lake also changes while the boat is passing. At this point, the marine authorities would probably request a clearer description. For many years, illustrations showed the heliosphere with a long, narrow tail resembling that of a comet. Some observations support the existence of an extended downstream region, often called the heliotail, but its full geometry remains uncertain. Different physical models can produce different shapes depending on how they treat magnetic fields, neutral atoms, solar wind structure, and the surrounding interstellar flow. Some suggest a long tail, others produce broader, shorter, or divided structures. The heliosphere may even contain lobes shaped partly by the sun's magnetic field. These possibilities do not mean scientists know nothing. They mean that a vast three-dimensional plasma structure cannot be reconstructed from a few measurements and one convenient sketch. Voyager 1 and Voyager 2 crossed the heliopause along only two paths. They are like two needles passing through different places in an enormous invisible object. Each path reveals valuable local conditions, but neither can trace the complete outline. To see more of the boundary, scientists use particles that travel inward from distant interactions. Energetic neutral atoms are especially helpful. They can form when a fast charge particle captures an electron from a neutral atom. Once the particle becomes electrically neutral, magnetic fields no longer guide it in the same way, allowing it to travel more directly across the heliosphere. A detector nearer Earth can record its energy and arrival direction. by collecting many such particles, researchers can build an all-sky map of distant regions they cannot photograph in ordinary light. It is little like standing inside a dark valley and learning about the surrounding hills by catching thousands of tiny messengers rolling down from different directions. The map is indirect and interpreting it requires physical models, but it offers something no single outward-flying spacecraft can provide: a view assembled from across much of the sky. NASA's Interstellar Boundary Explorer, known as IBEX, began creating such maps after its launch in 2008. Its observations revealed that the outer heliosphere changes over time, responding to variations in the solar wind that began much closer to the Sun years earlier. IBEX also discovered an unexpected band of enhanced energetic neutral atom emission stretching across the sky. This feature became known as the IBEX ribbon. It does not appear to be a solid structure floating at the boundary. Instead, it is a pattern in the arriving particles closely connected to the interaction between the heliosphere and the local interstellar magnetic field. Its discovery showed how much structure had been missing from earlier pictures. Even after years of study, the ribbon remains an important clue rather than a completely closed case. The outer solar system continues to offer mysteries without needing to hide a physical object behind every one of them. A newer observer has now joined this work. NASA's Interstellar Mapping and Acceleration Probe, or IMAP, launched in September 2025, reached its observing region near the Sun-Earth Lagrange point, known as L1, in January 2026, and began its primary science mission the following month. From there, its 10 instruments study the solar wind energetic particles, interstellar material, and neutral atoms arriving from the heliosphere's distant boundaries. IMAP builds upon the mapping methods developed by IBEX while measuring a wider range of particle energies and conditions. The mission does not look outward with a conventional camera and capture the heliopause as a glowing shell. Instead, it gathers particle by particle, direction by direction, gradually assembling evidence about how the Sun's domain changes and how energetic material moves through it. The finished maps will still require interpretation. Better instruments sharpen the question. They do not force nature to become simple. So the heliosphere moves through the Milky Way as a changing permeable structure, rather than a fixed bubble carried intact between the stars. Its shape depends on the solar wind leaving from within the interstellar medium pressing from outside, and magnetic fields extending through both. Its front flanks and possible tail need not share the same structure. Its boundaries can carry ripples produced by solar changes that began years earlier. And because our observations come from scattered spacecraft incoming particles and computer models, the full shape remains under investigation. Yet one distinction is already clear. The heliopause marks the outer reach of the Sun's wind-dominated plasma environment, not the outer reach of everything belonging to the Sun. Beyond this moving boundary, gravity continues quietly across distances far greater than the heliosphere itself. Crossing the heliopause does not switch off the Sun. Voyager entered interstellar space because the plasma around it was no longer dominated by the solar wind, but gravity obeys a different rule. It does not travel outward as a stream of particles, and it does not stop at the place where the solar wind meets the interstellar medium. This Sun continues pulling on every spacecraft, comet, planet, and grain of dust around it, no matter how distant they become. That pull weakens rapidly with distance, but it never falls abruptly to zero. So Voyager can be surrounded by interstellar plasma while still feeling the gravity of the star it left behind. This is one of the quiet contradictions hidden inside the phrase leaving the solar system. A spacecraft can cross one meaningful boundary and remain far inside another. The heliopause tells us where the Sun's wind loses control. It does not tell us where the Sun's gravity ends. Gravity weakens according to distance, which means its influence fades smoothly rather than breaking at surface. Move twice as far from the Sun, and its gravitational pull becomes 4 times weaker. Move 10 times farther, and the pull becomes 100 times weaker. The decline is steep, but there is no final distance at which the force simply disappears. Imagine a lamp shining across a dark field. Its light becomes harder to notice as you walk away. Yet there is no precise point where the photons receive instructions to stop. Gravity is not light, and the comparison should not be pushed too far, but both help us understand a fading influence without a hard border. The useful scientific question is therefore not where solar gravity becomes exactly zero. It is where the Sun's pull becomes less important than the combined influence of other stars in the Milky Way. Voyager is also not orbiting the Sun in the way Earth or Neptune does. Each spacecraft gained enough speed during its encounters with the giant planets to follow an open path outward. In orbital language, the Voyagers are gravitationally unbound from the Sun. This does not mean the Sun no longer pulls on them. It means their outward speed is sufficient that solar gravity cannot turn them around and bring them back into a closed orbit. As they travel, the Sun continues slowing them slightly, but not enough to reverse their escape. Picture a ball rolling up a very long hill with enough energy to pass over the top. The slope still resists its motion, yet the ball does not return. The comparison is imperfect because interstellar space contains no literal hill, and Voyager is not rolling on anything. Still, the idea is useful. Gravity continues acting even after escape has become inevitable. This distinction allows two statements that sound contradictory to be true at the same time. Voyager has entered interstellar space, and Voyager is still being pulled by the Sun. It has escaped a closed solar orbit, but it has not reached a place free from solar gravity. In fact, no such finite place exists. The Sun exerts a gravitational attraction on distant stars, and those stars exert one on the Sun, although the forces become extraordinarily small. Gravity is patient and not especially concerned with whether a spacecraft has crossed a boundary that matters to plasma physicists. At great distances, however, the Sun is no longer the only important influence. The gravitational field of the Milky Way acts on the entire solar system. Passing stars can disturb remote objects. The combined pull of the galaxy gradually competes with the Sun's ability to keep distant bodies securely attached. This is where the idea of gravitational ownership becomes less tidy. Close to the Sun, there is little ambiguity. Earth follows a stable solar orbit, and Neptune remains securely bound despite its great distance. Farther out objects can occupy increasingly fragile paths. A distant comet may take millions of years to complete one journey around the Sun, moving so slowly near the outer part of its orbit that a passing star or the tidal gravity of the Milky Way can alter its future. The Sun may still be the main object guiding that comet, but only gently. There is no fence separating a purely solar region from a purely galactic one. Instead, there is a broad transition where stable attachment becomes easier to disturb. Astronomers can estimate zones in which solar orbits may remain possible, but the answer depends on direction, time, the orbit itself, and the gravitational encounters that occur along the way. The heliosphere is tiny compared with this wider gravitational realm. Voyager crossed the heliopause after travelling a little more than 100 times the distance between Earth and the Sun. The Sun's distant population of possible comets may extend thousands or tens of thousands of times that Earth-Sun distance, perhaps farther depending on how the region is defined. This difference in scale is enormous. If the heliopause were placed near the edge of a small garden, the gravitational outskirts might lie far beyond the surrounding town. the comparison cannot preserve the true proportions without becoming inconvenient, which is often the fate of comparisons in the outer solar system. What matters is the separation of ideas. The solar wind boundary is relatively near. The gravitational frontier is vastly more distant, so we continue outward with the sun still behind us, visually reduced to one brilliant star among many but gravitationally present in every moment of the journey. Its wind no longer fills the space around us, yet its pull remains woven into the path of the spacecraft. Far ahead lies the region where that pull may hold enormous numbers of icy bodies on extremely long and delicate orbits. We cannot see this population as a complete cloud. We infer it from comets that occasionally fall inward from the darkness. These returning visitors offer our best clues to the distant reservoir that may surround the solar system far beyond the heliopause. To approach the sun's gravitational edge, we must follow the comet's home. The sun's distant comet reservoir cannot be seen as a complete cloud. No telescope has photographed a pale shell surrounding the solar system, and no spacecraft has travelled far enough to pass through its main population. The region we call the Oort Cloud is instead reconstructed from visitors that occasionally fall inward. These are long-period comets, icy bodies whose stretched orbits can carry them from the planetary region into distances so great that one journey around the sun may take thousands, millions, or even more years. When one of these objects approaches the inner solar system, sunlight warms its surface and releases gas and dust, creating the bright coma and tail familiar in photographs. For a brief time, a body from the solar system's darkest outskirts becomes visible. Then it may return to the cold for an interval longer than recorded human history. The comet is not merely an object in the sky. It is evidence arriving from a place we cannot yet visit. Unlike the Kuiper Belt, which forms a broad disk beyond Neptune, the Oort Cloud is thought to surround the Sun in something closer to a vast sphere. Its objects may approach from many directions rather than remaining near the plane of the planets. This pattern is one reason astronomers infer that a distant, roughly spherical population exists. The word cloud can be misleading, however. It is not a continuous fog, and its objects are not packed together like droplets in the atmosphere. They are likely separated by enormous distances, moving along delicate gravitational paths through almost empty space. Imagine a dark forest in which every tree stands many kilometers from the next. From far away, the collection might be described as a forest, but a traveller among the trees would spend most of the journey seeing open ground. The Oort Cloud is a population, not a visible surface. The objects in this reservoir are thought to be remnants from the solar system's formation. Many may have begun much closer to the young sun, among the developing giant planets. Repeated gravitational encounters with Jupiter-Saturn, Uranus and Neptune could have thrown small icy bodies onto distant orbits. Some escaped the solar system completely. Others may have been scattered far enough outward that the gravity of nearby stars and the young Milky Way altered their paths, lifting them away from the planetary plane and forming a more spherical distribution. This is the leading broad picture, but the details remain model-dependent. Astronomers do not know the exact number of objects, their total mass, or the precise structure of the cloud. Even its inner and outer boundaries are uncertain. The region is less a mapped destination than a gravitational explanation that successfully connects many distant comet orbits to the solar system's early history. Some models divide the reservoir into an inner region and a more distant outer cloud. The inner portion may be denser and more strongly attached to the Sun, while objects in the outer portion occupy extremely wide and fragile orbits. But these are not separate shells with polished boundaries. One population likely blends gradually into another. The distances involved are difficult to fit into familiar intuition. The heliopause crossed by Voyager lies only a tiny fraction of the way toward the farthest possible members of the Oort Cloud. Even travelling at the speed of our fastest outward spacecraft reaching the deeper reservoir would require a span of time far longer than a human lifetime. Passing through the entire region would take much longer still. The Oort Cloud may belong to the solar system, but it does not belong to human travel plans. The calendar once again has chosen not to cooperate. How then does an object leave this distant reservoir and become a comet visible from Earth? At such great distances, the Sun's gravity holds objects only gently. A small gravitational disturbance can change an orbit that would be almost impossible to alter closer to the Sun. The steady tidal influence of the Milky Way can gradually reshape these paths. Passing stars can also provide a nudge, especially when they move comparatively near the solar system over astronomical time. These disturbances may send an icy body inward, beginning a fall that lasts for an immense period before it reaches the region of the planets. Others may be pushed farther away or removed from the Sun entirely. The Oort Cloud is therefore not a frozen vault whose contents remain untouched. It is a slowly changing frontier where the gravity of the Sun and the wider galaxy are already working together. Not every long-period comet offers a simple map back to its birthplace. A comet's orbit may change when it passes near a giant planet. Jets of gas escaping from its warming surface can add tiny non-gravitational pushes. Some comets break apart, fade, or are ejected after crossing the planetary region. Astronomers must reconstruct their earlier paths carefully, accounting for these effects and for the uncertainties in each measurement. Even then, the original orbit may not identify one exact location in a distant cloud. It provides a statistical clue rather than a return address. By studying many comets, scientists can test models of the reservoir that supplied them. The evidence is persuasive enough that the Oort Cloud has become a standard part of our scientific picture of the solar system, but it remains inferred. We know it through consequences, not through a complete view. Here the meaning of the solar system's edge becomes especially soft. An Oort Cloud object may still orbit the Sun, but its path can be reshaped by the Milky Way or by a passing star. The Sun remains its primary gravitational partner, though not an unchallenged one. Farther outward, stable solar orbits become increasingly vulnerable, and the distinction between belonging to the Sun and belonging to the galaxy begins to blur. There is no final row of comets marking the border. There is only a thinning population held ever more loosely as other gravitational influences grow important. We have travelled beyond the planets, the Kuiper Belt, the solar wind, and the heliopause, yet the solar system still refuses to end cleanly. To find its farthest meaningful frontier, we must now enter the region where the Sun's gravity meets the larger pull of the Milky Way. At the farthest reaches of the solar system, the Sun does not meet the galaxy at a single line. Its gravity becomes gradually entangled with the gravitational environment that has surrounded it all along. Every planet, comet, and spacecraft moves not only around the Sun, but also with the Sun as it travels through the Milky Way. Close to our star, solar gravity clearly dominates the local motion. Earth completes its yearly orbit. Neptune follows its slower path, and the planets remain securely organized around one central mass. Far beyond them, the arrangement becomes less certain. An object in the distant Oort Cloud may still follow the Sun, but its orbit can be so wide and slow that the wider galaxy begins to reshape it. The final frontier is therefore not a place where solar gravity disappears. It is a region where the Sun is no longer acting alone. The Milky Way's influence is sometimes described as a galactic tide. This does not mean an ocean is flowing through the Oort Cloud. It refers to the small difference in the galaxy's gravitational pull across the enormous scale of a distant comet's orbit. The Sun and comet are both falling through the gravitational field of the Milky Way, but they do not occupy exactly the same position, so the forces acting on them differ slightly. Close to the Sun, that difference is far too weak to disturb a planet significantly. At Oort Cloud, distances where solar attachment is much more delicate, the same slow effect can alter the shape and orientation of an orbit over immense periods. A comet's closest approach to the Sun may gradually move inward or outward. Its orbital plane may turn. A body that once remained safely in the distant reservoir can eventually begin a long journey toward the planets. This can be pictured as a small boat anchored in a broad tidal current. A short, strong anchor line keeps the boat close and leaves little room for the current to change its motion. A very long and loose line allows the same current to pull the boat into a much wider path. The Sun's gravity is not an anchor cable, and galactic tides are not water, but the comparison captures the growing vulnerability of extremely distant orbits. The farther an object travels from the Sun, the more slowly it moves near the outer end of its path and the more time weak disturbances have to accumulate. No single moment needs to be dramatic. A slight change repeated over millions of years can become important. The galaxy works slowly here, which is convenient because the Oort Cloud appears to have no urgent appointments. Passing stars add less regular disturbances. Stars do not remain fixed in the patterns of our constellations. Each follows its own orbit through the Milky Way, and over long periods some pass comparatively near the Sun. Even a star that remains far beyond the planetary system can gravitationally disturb the outer Oort Cloud. Depending on its mass, speed, distance, and direction, it may gently change the paths of distant comets. Some objects can be pushed into tighter solar orbits. Others may be nudged toward interstellar space. Most stellar passages do not produce a spectacular event, and the effects on individual bodies are difficult to predict because the cloud itself has never been fully mapped. Still, such encounters are a normal part of living inside a galaxy filled with moving stars. The solar system is not an isolated clockwork model kept beneath glass. The boundary also changes with direction. The Sun's ability to retain an object depends on the object's orbit and on the surrounding gravitational field. A comet may remain stable along one kind of path, while another orbit at a similar distance becomes easier to disrupt. The galactic tide does not pull equally in every direction, and a passing star can temporarily reshape the region of long-term stability. This is why a single spherical distance cannot provide a permanent gravitational edge. Astronomers can estimate a broad domain within which solar orbits are possible, sometimes using concepts that describe where the Sun's attraction dominates relative to the galaxy. But the real frontier is neither perfectly spherical nor fixed for all time. It breathes on astronomical timescales as the Sun moves stars pass, and distant objects follow their fragile paths. We might imagine the Sun and nearby stars surrounded by overlapping pools of lamplight. Near each lamp its own glow is strongest. Farther away the light weakens until illumination from other lamps becomes comparable. There is no dark stripe separating one pool from the next. Gravity is not literally light, and gravitational influences add together rather than simply replacing one another, but the image preserves an important truth. The Sun does not possess a private sphere cut cleanly from the Milky Way. It creates a region of strong local organization inside a larger gravitational system. Beyond the most secure solar orbits, an object's future may depend on several influences at once. It can remain loosely associated with the Sun while already responding to the structure and motion of the galaxy. This also means that the outer edge of the solar system changes with time. A distant comet that appears securely bound during one era may later encounter a passing star or accumulate enough orbital change from the galactic tide to begin moving inward or outward. other objects may be captured from the surroundings, although such exchanges are difficult and depend on the circumstances of stellar encounters. Over the age of the solar system, its farthest population has probably been eroded, replenished, and rearranged. The frontier is not a row of ancient objects still occupying their original positions. It is a slowly evolving transition between solar and galactic dynamics. Even the concept of belonging becomes temporary when an orbit lasts millions of years and passes through a neighborhood of moving stars. We have now crossed every major meaning of the word edge. The large planets ended near Neptune, but smaller icy worlds continued. The fast solar wind slowed at the termination shock and passed through the heliosheath before yielding at the heliopause. Interstellar space began there, yet solar gravity continued far beyond it. The possible Oort Cloud extended that gravitational story into a region where the Milky Way and passing stars could gradually alter the paths of solar objects. At no point did we find one final wall. Instead, each form of the sun's influence faded according to its own physics. From here we can begin the quiet journey home, gathering these boundaries into one clear answer and returning to the small world from which the question began. The solar system has no single edge, because the sun does not influence space in only one way. If we define our home by its major planets, the familiar system begins to fade beyond Neptune. If we define it by the flow of particles from the sun, the relevant boundary lies much farther away at the heliopause. And if we define it by gravity, the solar system may continue through a vast and uncertain reservoir of distant comets before blending into the wider gravitational environment of the Milky Way. None of these definitions is wrong. Each answers a different question. The mistake is expecting them all to produce the same line. Nature has given us several boundaries, each made by a different physical process, each meaningful for a different reason, and none resembling the clean circle that once surrounded the planets in a classroom diagram. Let us look back across the path we've travelled. Near the Sun, the major planets form the most obvious architecture. Their large bodies, regular orbits, and familiar names give the solar system its recognizable shape. Beyond Neptune, however, the planetary sequence gives way to the Kuiper Belt and more scattered populations of icy worlds. Pluto is not a gate at the edge. It is one member of a broad and distant frontier. Farther out, visible objects become increasingly difficult to find, but the Sun continues filling space with its solar wind. That flow eventually slows as the termination shock passes through the disturbed heliosheath and reaches the heliopause. Beyond that boundary, the surrounding plasma belongs mainly to the interstellar medium. We've crossed from the Sun's wind into the material between the stars. What we know is already remarkable. Voyager 1 and Voyager 2 measured this transition directly along two different paths. Their instruments detected changes in particles plasma and magnetic conditions that showed they had entered interstellar space. We also know that interstellar space is not empty. It contains thin gas dust energetic particles and magnetic fields, all belonging to the Milky Way through which the Sun is moving. The heliosphere exists because the solar wind presses outward into this surrounding material. It is a changing shelter rather than a permanent shell shaped from within by the Sun and from outside by the galaxy. Its boundary can move and its complete form remains difficult to reconstruct. Still, the essential transition is clear. Beyond the heliopause lies another environment, not an absence of environment. The evidence also suggests that the Sun's wider gravitational family extends enormously farther. Long-period comets arrive from many directions on orbits so large that they point toward a distant, roughly spherical reservoir. We call it the Oort Cloud, though no telescope has photographed it as a complete structure. Its possible members may remain loosely attached to the Sun across distances far greater than the heliosphere. At those distances, their orbits become vulnerable to the tidal gravity of the Milky Way and to the influence of passing stars. Some are nudged inward and eventually appear in our skies as comets. Others may be pushed outward and lost. The Oort Cloud is therefore not a final frozen shell. It is a slowly changing transition where the Sun's gravitational organization begins to merge with the motions of the galaxy. Much remains uncertain. We do not know the exact shape of the heliosphere in every direction. We do not know precisely how its distant tail is arranged, or how every part of its boundary changes over time. We do not know the exact number of objects in the Oort Cloud, its total mass, or where its outer population should be said to end. Even the gravitational frontier depends on what kind of orbit we're considering and what disturbances occur across millions of years. These uncertainties do not mean the journey has failed to find an answer. They are part of the answer. An edge formed by competing influences cannot always be expressed as one permanent distance. Sometimes science becomes more accurate by replacing a sharp line with a region and a simple ending with several overlapping transitions. Now we can allow the distances to fold gently behind us. The fragile outer comets fade first, becoming only possible points in a darkness shared with nearby stars. The heliopause passes around us without light or sound. The slower plasma of the heliosheath gives way to the faster solar wind. Frozen bodies appear again scattered across the broad region beyond Neptune. Then the large planets return one by one, small at first, then familiar. Neptune, Uranus, Saturn, Jupiter, Mars, Earth. The sun grows from a bright star into the warm light that defines the days of one small world. What lay beyond the edge of our solar system was never a single secret place. Beyond one edge were icy worlds. Beyond another was interstellar matter. Beyond another was the gravitational landscape of the Milky Way. The solar system did not end by vanishing. It faded into something larger. And perhaps that is the quietest way to think about our place here. Earth is not enclosed inside a perfect cosmic border. It moves with the sun through material shaped by older stars, while particles from the galaxy pass around and sometimes through the sun's invisible domain. Our planetary home is distinct, but it is not isolated. Its boundaries breathe exchange matter and respond to the universe beyond them. The room around you remains still. The planet beneath it continues around the sun, and the sun continues carrying every world in its care through the Milky Way. Far beyond Neptune, its influence grows weaker, layer by layer, until the idea of an edge becomes less useful than the idea of a gradual belonging. There is no final wall to reach, only a slow transition from one home into another. And for tonight there is nowhere else you need to travel. You can let the distant boundaries fade, allow the stars to remain quietly beyond the window, and rest here beneath the sun.